Hello, my name's Alan Foom, and this is the fourth part of my talk on Fairway Evaluation. Today I'm going to focus on building common risk segment maps. This is how we risk exploration prospects. Now, all the elements must work. So you have your source, your reservoir, your seal, your trap, and your charge. All of them have to work. If any one of them fails, you'll get a dry hole. Now, within Fairway Evaluation, we look at the source, the reservoir, and the seal. Charge is somewhat localized because you have to get the hydrocarbons from the source into the prospect, and trap is obviously very prospect dependent. So what we do is we map these three elements within common risk segment maps. So next few slides will demonstrate how you do this, and this is based on a fictional basin, so I made all this up, data up. So building common risk segment maps, and then combine common risk segment maps to end. And then we'll look at how these things are risked. So this is a fictional basin. So you can see you have green are the successful wells, the blue are the dry holes able to play, and the yellow wells are bypass wells. So these are wells that are drilled at other plays that go through the same stratigraphic interval and still give you valuable data. This gives you an idea of what your seismic database looks like. So you have fairly good 3D coverage in here. Now, there wasn't always 3D coverage. There would have been initially a lot less data, but this is what you are now. Then you have dense 2D coverage around that, and then relatively sparse 2D coverage going towards the east. So this gives you an idea of the database that you have to work with. Again, very important because the database gives you an idea of how certain you're likely to be. So looking at this particular reservoir unit, in this particular case you have a shore face sand, something like the Full Mine North Sea equivalent of. So the basin waters to the east, you have the shore face here in yellow, then you have the coastal plain in green, then you have outcropping basement, so this effectively is the continent, and then here you're going into the offshore mud, and then you're going off into the deeper water. Now, there could well be other plays, for example turbidites from low stand fans that come off here, but in this particular case we're looking at the shore face which is confined to the yellow area. Then you're looking at your source kitchen. Now, this is the source kitchen is underneath the reservoir from a different formation. Dark grey areas where the source rock is present, and the light grey area is where you think it might migrate to. This could be based on a basin model. This could be based on something a little bit more simplistic like the spreadsheet model. The basin model is obviously best, but takes a long time to build and takes effort to build, but gives you valuable results. And then you're looking at seal potential. So the dark blue area are laminated shales, which are relatively thick, low permeability like the seal. Lilac area, thinner mudstones, perhaps a bit of local erosion, more potential for leakage, and the red area, the seal rock is absent. So you have an idea of where things are from your depositional environments. You then move to common risk segments. So in this particular case, you're looking at reservoir. So the green area is your shore face sand. The yellow area is your coastal plain. You know, the channels within that, the shore face can migrate a little bit, but relatively low chance of success. And then your red areas are where this particular reservoir is absent. Now, there are other reservoirs in these areas, but we're not talking about them. We're just talking about this one. So green is good, amber, possible, red, highly unlikely. Then you're looking at your source map. So again, if you remember before, we had the grey blob and a light grey blob. We have potential for hydrocarbons to be generated. We have your kitchen and then your migration oriole. But again, migration area is a bit uncertain. Could be a little bit more this way, could be a little bit more that way. So you have an amber ring effectively around your green blob. And then the red are areas where you feel the hydrocarbon charge is extremely unlikely. And then going to the seal, you've got a situation where the green blob is your laminated shales. You're likely to be good seal. Yellow is, well, we're not entirely sure where the boundary is, so it could be here, could be there. And then the red are the areas where you think it really is going to likely to be absent. And you will use your well failure analysis within this. So if these wells were drilled at the play and they failed because you felt that they failed due to seal failure, that's further evidence. Then you build something called a combined common risk segment map. So this effectively is a confluence of the green blobs. So you have where you think you're likely to have seal, you think where you're likely to have source, you think where you're likely to have reservoir, and then you have the green blob where all three of them coincide, and this is where all the fields actually are. Now, if you happen to have a field that's outside the green blob, well, you've got to change the green blob because something somewhere has not been estimated quite right. Now, the polygons where some of these things are, some of these are uncertain, but new data may either grow or shrink the sweet spot. So these things need to be updated as new information comes in because these are not static. It's very dangerous to be seduced by green blobs. So how do you make that into risk? How do you assign things? So there's several ways of doing it. Traditionally, prospects are risked individually. So you have a reservoir risk, a trap risk, a seal risk, a source risk, and a charge risk, all put together. All of them have to work. All these are probabilities between 0 and 1. So where 1 is certain and 0 is where it's not going to happen. In reality, risk factors are never quite that polarized because obviously you have information, so information that is uncertain. So people would use play fairway mapping to bias the risk, to guide it and change check, but in a qualitative way, but never do it quantitatively. So that's one way of doing it. The other way of doing it is when you combine the play and prospect. Now this can go down a bit of a rabbit hole because it can induce complexity, the possibility of double risking. In this particular case, you have reservoir risk for play, charge risk for play, seal risk for play, trap risk for prospects because that's prospect specific, times a reservoir risk for prospects, so that's a modifier to your play risk. So let's say if the play risk is very high, but you've got some ambiguities locally, you'd put that into a prospect. Then your charge risk for a prospect, then your local seal risk for a prospect. You can see from that there's a perceived chance of double dipping. If you think something's negative in the play and something negative in the prospect, you can end up with a severe underestimation because you're just risking the same thing twice. Also, where do you assign things? Is this a play assignment or is this a prospect assignment? People can argue about this for a long time. And also, how would the different impacts have? So how would the well have on other things? So, for example, if there are prospects nearby, how would they be impacted by this particular well? So one way of doing it is doing the risking is assigning play risk. So this is a matrix which is based on work by various people. So effectively something which is where a high risk, a high chance of success, a low risk is 0.8, medium chance of success is 0.5, and low risk is 0.2. So bracketed, but still there. So the green blob would represent high chance of reservoir, high chance of seal, high chance of charge. So 0.8 times 0.8 times 0.8 is 51%. Now, for a lot of people, that doesn't actually sound like very low risk, but this is exploration. And something where everything looks negative would have a chance of success of less than 1%. So you'd start writing these areas off, but you still look at some of these. And the risks would then be modified by individual prospects. So let's say if you're in the high risk, if your prospect is in the high chance of success area, where the baseline is 0.8, you may modify it to 0.9 with good local indications, or 0.7 with slightly poorer local indications. If it starts getting lower than that, then you're kind of not really in the high zone anymore. You need to change your overall point of view. So risks would be modified in that way. So that's one way of looking at it. Another way of looking at it is adding uncertainty. Now, data is never certain. So for example, here we have the 95% area where play element is good, high confidence, good data control. So this is per single element. You obviously got to do this for all the other elements. Play element good, moderate confidence, medium data control. Play element believed to be good, but you've got lower confidence and less data. And then here you have the mediums, where here you don't really know. Here you know something, but you're still confused. And here you know a lot, you still don't know what the heck is going on. And here is for poor. So this is a situation where you've got poor element, belief, high confidence that you really think it's not going to work, and good data control to back it up. So this is looking at it in a slightly more probabilistic way, taking the element of uncertainty within that. So to sum up is basically beware of the green blobs. Play fairway mapping enables geologists to better understand the target play, puts the prospects into context, makes a consistent evaluation focusing on the key risks because you're now beginning to understand what they are. The maps are good visual tools to see where things are, and enables your focused evaluation with limited resources. Limited time, limited people, limited data. But it's still a geologist's interpretation, with all the limitations, uncertainties, caveats that inherent in any Earth model. A model should change when the new data comes. People can get very fixated on their models and don't like it when data comes in and it disproves them. But we must not be fixed by green blobs. New data comes, got to change your mind. Thank you very much.